Ok, todas que estão aqui presentes, iremos dar início às palestras no segundo Encontro Internacional de Ciência e Engenharia de Materiais e segunda Conferência Internacional de Cooperação entre Indústria e Academia. Como primeira palestra, nós temos o professor Abu Kabir. O professor Abu Kabir, ele é do Departamento de Engenharia Mecânica e Aeroespacial da Universidade de Carleton, em Ottawa, no Canadá. Ele tem pós-doutorado e doutorado pela McGill University, no Canadá, e vasta experiência internacional, e estará apresentando o trabalho intitulado Eliminação de trincas de solidificação durante a fusão por poça em solda de uma liga de alumínio 7075, tá? Por nanopartículas de carboneto de titânio que está dentro do filamento de solda. Dear Professor Kabir, you are ready. If you are ready to start, okay, you can start as wish.
All right. Thank you, Professor Rodriguez. So please let me know when to stop for the translation. Hi, morning. It's very early in the morning in Ottawa. Initially, I thought it's going to be 7:30 in the morning, but we had the daylight savings when it started, so it's actually 6:30 in the morning. So I'm Abu Said Kabir. I'm an associate professor in the Department of Mechanical and Aerospace Engineering here at Carleton University in Ottawa. So the work that I'm going to show you today will be kind of like, let's say, at the infant stage of this work. It's done by one of my PhD students, Mr. Ali Reza Abdullahi. And this work is also co-supervised by Professor Michel Nganbe from University of Ottawa. And the topic for my presentation is eliminating solidification cracks during fusion welding of Aluminium 7075 alloy with titanium carbide nanoparticle enhanced filler metal.
You can go ahead.
Oh, okay. All right. So speaking of aluminum, it's about 8% of the Earth crust is aluminum, making it the most abundant metal on the planet. However, it's always found combined with various other alloying elements, right? It's never by itself in pure state. But once we can get it in pure state, we can alloy it with different kinds of metals like zinc, copper, magnesium, manganese, and silicon. And we can create different kinds of alloys with that one. And with different kinds of alloys, we can get different kinds of microstructure, so as different kinds of properties. It's a wide range of properties that we can get with aluminum alloys. I can continue, right?
Ok, e tem vasta explicação, então essas ligas de alumínio elas também estão alguns outros elementos químicos como zinco, cobre, magnésio, manganês, sílica, tá? Faz parte, são outros metais que podem ser ligadas e tem uma grande gama de aplicação, dependendo da composição e microestrutura.
The extraction of aluminum was so difficult, speaking about a little bit of history of aluminum alloys, that the extraction of aluminum was so difficult during the early 19th century that it was more precious than gold, right? Story goes that Emperor Napoleon III reserved a prized set of aluminum cutlery for a special guest at banquets. And the less favored guests used gold knives and forks.
A liga de alumínio, ela, em 1952, ela...
Well, the very first Wright brothers aircraft was mostly made of wood and bamboo frame connected, or let's say covered with canvas. Now, the aircraft needed to be very light due to limited engine capacity, and there was simply no metal light enough on that time to do that. And at the same time, the aluminum was available, but was prohibitively expensive. So most of the aircrafts, what we see before or during the World War I war era, was made of woods, actually.
Okay, so you can go ahead.
All right. So actually, during the time of World War I and World War II is the time when the use of aluminum became really, really versatile, and especially in the aerospace industry. And another significant history in aluminum industry is the early 1900 is when Alfred Wöhlm discovered, which was accidentally, the edge hardening of aluminum 4% copper alloy. Okay. Now, he actually created the new wonder materials of the world by accident.
Okay, you can go ahead all your presentation. At the end of the presentation, I'll be here for the question answer. Okay, you can go through the English. Okay, go ahead.
That's very good. All right. So just to show you some of the major, like most important applications for aluminum. 15% of the world's aluminum used by the energy sector. Even though copper is a better conductor, all main overhead power lines use aluminum as the conducting materials. Now, to carry the same amount of electricity, or let's say current, as a copper wire, the aluminum wire needs to be 1.5 times thicker, but yet still is 2 times lighter than the copper. So this decrease in load on these filings and allow the spans between them to increase dramatically. This saves a lot of money on construction of these overhead lines. Now, speaking of construction, it is one of the largest. This industry, the construction industry, is one of the highest user of the aluminum alloys. So almost 23% of aluminum goes in the construction industry. The example here is the Empire State Building is being built somewhere in 1930 and 1940, and it is one of the earliest skyscraper to use aluminum extensively because of its corrosion resistance and its lightness. So it was the perfect material for exterior framing and roofing. Speaking about automotive industries, so automobile industries are adopting aluminum alloys very fast. You can see the curve going straight, literally straight up. And aluminum is replacing the steel. Okay, so there is an example here published in Aluminum Insider that these days, in current days, a SUV weighs about 1.7 ton. But within next 3 or 4 years, an SUV will weigh about 1.2 ton. That's about almost 500 kilograms of weight savings. And how are they going to do that? They're going to increase the amount of aluminum significantly. Look at this. There's still, in today's SUV, we have almost 60% steel in here. But they're gonna use about 30% steel, and they're gonna replace it with 37% aluminum. Of course, there will be other materials like 4% magnesium in there as well. But aluminum is the one that will replace most of the weight. And it's very important for the fuel efficiency of the car. Now, I have to talk about the history of aluminum in aerospace applications because that's what my interest is. That's my primary concern. As I said, I'm from mechanical and aerospace engineering, so this is my primary concern. Little history about aluminum in aerospace. So, as I mentioned, the Wright brothers aircraft, although it was made of wood and reinforced steel, the engine was made of aluminum alloy. Okay, actually, the Wright brothers, they developed, designed, and manufactured this engine themselves. Okay, at that time in early 1900, the automobile, the only engine available was the automobile engines, but they were made of steel and they were extremely heavy, and they did not provide enough power to achieve the takeoff. So the Wright brothers literally manufactured that engine from aluminum copper alloy. So the story says that they didn't want the people to know that the engine was made of aluminum alloys. Therefore, they coated the crankcase with black color so that nobody knows what it is made of. Then in 1915, the German aircraft designer Hugo Juncker, they built the first full metal aircraft. So this is the Second World War era. It's a monoplane. Literally, the whole plane is made of aluminum alloys. Okay, but it didn't really fly. Okay, it was just a prototype. In commercial aerospace applications, you see the aluminum is the leading materials up until last 10 years. I would say when Boeing 787 and Airbus 350 came out. Before that, the gray color is for aluminum. You can see 747, 737, and 777. This is an example for Boeing. The majority of the structure was made of aluminum alloys, and recently they've been the carbon fiber reinforced composite took over that area, right? But still, in military applications, the military aircrafts, the aluminum is the primary one. In space industries, NASA Space Shuttle, this primary fuel tank and the secondary boosters, they're all made of aluminum alloys. The recent aircrafts like SpaceX Falcon 9, Falcon 9 Heavy, they are all made of aluminum silicon alloy. I'm talking about the outer structure. It's made of aluminum lithium alloys. So it is, aluminum is one of the most important engineering materials. Now, talking about aluminum in these alloys, so as I mentioned, that different kinds of elements can be added with aluminum to create a wide range of chemical and mechanical properties. And based on that alloying addition, the aluminum can be classified on 7 different classes. Okay, I lost that. Okay, so if we...
Professor Abu, pessoal, até agora a apresentação, ele falou toda a aplicação das ligas de alumínio, falou do histórico. Vai falar agora sobre a principal, a liga de alumínio que ele está pesquisando. Se você ver, nós temos a categoria das ligas de alumínio, tá? Nós temos o alumínio, as classificações 1XX é só o alumínio, tá? E as classificações de acordo com o elemento químico, tá? Que você vê, ele tem a numeração, tá? Então ele está focando, ele vai mostrar qual que ele está fazendo pesquisa dessa liga especial de alumínio. Go ahead.
Okay, so depending on the alloying addition, we classify the aluminum alloys in 7 different classes. So 1000 series, 3000, 2000 series, 3000, 5, 6, 7, and we have the 8000 and 9000 series as well. The 8000 is aluminum lithium, and 9000 is still under development. So you can see that 135,000 series, they are strain hardening alloys. Okay, so
perceber a classificação de 1000, 3000, 5000 são alumínios que têm endurecíveis, ligas de alumínio endurecíveis. Go ahead.
And this is our interest. So we want to talk about the edge hardening alloys. That's the 2000 series, 6000 series, and 7000 series.
Vamos falar sobre essa classificação desses 3 últimos, que são as ligas que elas passam por um processo chamado edge hardening, e vai focar nessas 3 classes, chamadas classes de alumínio.
And we will target this 7000 series particularly because it is the strongest aluminum thus far it can create. So we will study the fusion welding of 7000 series alloy.
A pesquisa está focada principalmente nessa classificação do alumínio com zinco, que tem a classificação de 7000, é um que tem altíssima resistência.
And the most popular 7000 series is Aluminium 7075. And
E essa liga é alumínio 7075.
the chemical composition shows that it has about 5 to 6% zinc, 2 to 3% magnesium, and about 1.2 to 2% copper.
A composição química dele principalmente está focado entre 5.1 a 6.1 de composição química, e tem outros elementos como magnésio, cobre, cromo, etc.
As we have a very high amount of alloying elements in the 7075, depending on the heating and cooling cycle, we get different kinds of intermetallic phases. So we can see there could be beta phase, the T phase, the eta phase, the theta phase, and the S phase. All can form simultaneously, or some specifics can form at the same time, depending on the heating and cooling cycle.
Como essa liga de alumínio ela tem muitos elementos químicos, ela acaba formando muitas fases intermetálicas, como a fase beta, teta, e etc. E isso acaba influenciando em todo o processo da fabricação dessa liga.
Now, the reason why we are so interested about 7075, this is a very simple comparison between 7075 at the peak hardness or T6 heat treatment and the AISI 1020 carbon steel. This is the mildest steel possible. We see that we can actually get at the peak hardness or peak strength position, we can get higher yield strength, higher UTS, higher hardness, and even better elongation than 1020 carbon steel. Whereas if you look at the density, it's about 1/3 of steel. So that makes a big difference in transportation industry, especially aerospace and automobile industry.
Você consegue perceber dessa liga de alumínio, ela tem propriedades muito maiores que a liga de aço 1020, por exemplo. Ela tem limite de escoamento acima do aço 1020, limite de resistência acima 572, e o que é interessante, até a ductilidade, você percebe que ela é comparável com a liga do aço 1020, essa liga de alumínio. Mas o que é mais importante para a aplicação aeroespacial é que essa liga, olha a densidade dela. A densidade dela é muito baixa em relação à densidade do aço.
Now, still, we know that 7075 has better strength than some of the mild steels, but still the application is limited because of the weldability, especially during the fusion welding. So this plot says which aluminum alloy is weldable and which one is not. And you see there is a big red block here on 7000X. It says it's not weldable in fusion welding. Okay.
Com relação às suas aplicações, você percebe que, apesar dessa liga de alumínio ter várias aplicações, ela tem muitas restrições. Uma das principais restrições para essa liga de alumínio, o único problema é a questão da soldabilidade. Você percebe ali naquele gráfico de retângulos que essa liga ela está vermelho, ou seja, quer dizer que ele não é uma liga que ela tem boa soldabilidade. Então, ela tem as suas limitações de aplicação, inclusive por propriedades boas, mas ela tem essa limitação na fabricação.
And we can see why, because people have tried to fusion weld aluminum 7075 alloy so many times, and every time they came back with this kind of examples, like a lot of cracks here and there. You can see almost all the images. There is a big crack right in the middle. So it's the solidification cracks that we get, and it is the most common in 7075, and that's the only reason that makes the 7075 unweldable in fusion welding.
E aí, como vocês veem na foto, o problema maior dela é a questão da propagação de trinca central que acontece no cordão de solda. Então, isso faz com que essa liga ela tenha suas restrições com relação ao processo de soldagem por poça de fusão. Então, vocês percebem aí que as trincas ela é central, você tem várias aplicações, e isso limita muito o uso dela, apesar das ótimas propriedades e baixa densidade.
Yeah, a little about solidification cracking, why it forms, because, well, as I mentioned before, that 7075 has significantly high amount of alloying elements.
E um dos problemas que acontece essa trinca, como ele já falou, é devido ao alto número de ligas, elementos de ligas que tem nessa composição química dela.
Due to the presence of this high amount of aluminum elements and formation of so many different kind of phases during the solidification, and some of the phases has very low melting temperature compared to others, like let's say eta phase that I showed you in previous slide has melting temperature about 420 degrees Celsius compared to aluminum itself, which is approximately 650 degrees Celsius.
O que acontece principalmente devido que forma muitos precipitados, então esses precipitados eles têm pontos de fusões diferentes da liga de alumínio em si, ou seja, tem as diferenças de até 200, 400 graus Celsius do ponto de fusão de um precipitado para outro, então tem regiões que solidificam mais rapidamente e outras não, então causando esse problema de trinca.
So when the weld head, or let's say the arc moves, the melt pool moves in the welding direction, it leaves a mush region, which is a mixture of the solid and liquid, like a two-phase region. And within this mush region, some of the phases get solidified, so it's solid, and some of the phases still remains as liquid.
É o que acontece, ou seja, num processo de fusão, nós temos aqui fases líquidas, que se prefere que a fase líquida solidifica, mas o que acontece é que umas se solidificam, outras continuam líquidas e acontece esse problema de trinca.
And those liquid areas, they create a crack because of the thermal expansion and contraction that left behind after welding.
Essas regiões líquidas, elas conseguem, ou seja, as trincas surgem justamente dessas regiões que estão ainda líquidas devido ao alto coeficiente de expansão térmica delas.
So we end up with a large solidification cracks like this one.
O que leva a vários problemas de trincas de solidificação.
Solutions to that, one very popular solution to this problem is that
soluções é uma solução muito popular que eu vou mostrar agora.
Yeah, we don't really use the fusion welding to weld 7075. Let's use solid state welding, like friction stir welding or linear friction welding. Just get rid of the weld pool, normal liquid metal.
Então, dos problemas não se usa para esse tipo de liga o processo de solda normal, tá? Por força de fusão. Então, usa o que nós chamamos de steel welding, que é um processo de soldagem. Ele vai mostrar depois aí diferença muito grande em preço também.
Or we can control the welding parameter. So optimizing, so if we control the fusion welding parameter, we are never going to get rid of the solidification cracks completely. It's impossible. If we change it to solid state welding process, the system becomes, application is limited, and it is very, very, very expensive because the friction stir welding process is very expensive itself. And the third way we can do that is by optimizing weld composition, which was not effective either.
Algumas das soluções que foram propostas é otimizar o processo de fusão, os parâmetros de fusão, o que não teve um efeito completo. Mudar os métodos, né, o que isso se torna muito limitado e muito caro. Também a composição química também não foi efetiva. E além ou seja, não teve muito sucesso com relação aos métodos tradicionais, tão limitados, tá? Não eliminou completamente as trincas de solidificação.
So there is a recent study published in Nature Materials, I believe, recently, a couple of years ago. They proposed a solution that if you add nanoparticles in the melt pool, in 7075 melt pool, you can actually eliminate the solidification crack completely.
Então, tem uma publicação do 2019 na Materials, da Nature Materials, em qual ele propõe que se você colocar nanopartículas, tá, na pulsa de fusão, você consegue eliminar essas trincas de forma efetiva.
Now, this is what they published. Okay, so they welded 3 different aluminum 7075 sheet metal, one with conventional 7075 filler metal, so the base metal and filler metal are same. They used aluminum 5 magnesium filler metal, which is a very conventional type filler metal that generally used to weld 7075. And in the third way, they used aluminum 7075 filler metal, but that filler metal was incorporated with 2.4 weight % titanium carbide nanoparticle.
Você perceber, nós temos aqui as três figuras que mostram. A primeira mostra o processo de solda normal que se aplica, você percebe que é solda. E aí, no caso, nós percebemos também na figura C que o novo, ou seja, o cordão, o metal de adição vem incorporado com 2,5%, tá, de nanopartículas de tamanho de 40 a 60 nanômetros de carboneto de titânio na liga de alumínio 7075.
And the image shows the output of the welding process. You see a big solidification cracks right in the middle on the first image when they use 7075 filler metal. There's a big solidification crack when you use the aluminum 5% magnesium. But look at this one, 2.48% titanium carbide nanoparticle infused 7075 filler metal. Absolutely no cracks at all. So they were able to eliminate the solidification crack entirely by the use of 2.8% titanium carbide nanoparticles.
Vocês verem, então, ele quando usou o filamento, a adição, metal de adição, com esse percentual de 2,7% de carboneto de titânio, ou essas nanopartículas, eliminou totalmente a trinca de fusão quando está comparado com as figuras A e B, ou seja, C eliminou totalmente essas trincas de fusão.
So what was the proposed solution? What did really happen when you add titanium carbide nanoparticle in there? So according to that paper, what happens is that the grain morphology changes in the fusion zone, so from columnar to equiax grain. And at the same time, there is some kind of modification in secondary phases as well.
Ou seja, uma das observações que foram feitas lá no artigo é que esse novo material, ele mudou a morfologia granulométrica da zona de fusão e também mudou as fases, tá? Mudou as fases secundárias, modificou as fases.
So the paper doesn't really explain that. Well, it's a legendary paper because it's the first time somebody said that they can eliminate solidification crack. I believe that's the reason it was published in Nature Materials, and it definitely worthy to be published. But the paper doesn't really explain how the mechanism works in the proposed solution.
Ou seja, tem essas soluções propostas, mas como sabe, é um artigo, né? Ele não diz por que aconteceu essa eliminação de trincas, né? Então, é um artigo publicado, porém, não diz lá os detalhes.
So we decided to reproduce that work and explain the mechanism. What exactly are the mechanisms behind this elimination of solidification cracks?
Então, nós decidimos reproduzir os experimentos para entender por que a causa dessa eliminação dessas trincas de solidificação.
So we did experiments almost the same. We had a 3 millimeter thick 7075 T6 sheets, and we bought the filler metal from the same company, and that was enhanced with 1.78% titanium carbide nanoparticles. We did butt welding with tungsten inert gas welding, and we used some welding parameters, but this is the main one, heat input, which was almost 0.7 kilojoule per millimeter, which is considered to be very high heat input. Okay, I'll come back to this one. Then we did some microstructural characterization with optical and scanning electron microscope. We did phase identification with XRD, and we did the tensile testing and did the thicker micro indentation hardness testing.
Então a gente decidiu fazer todos os experimentos, usar experiência similar que foi o paper, né, que foi publicado. Usamos uma chapa de alumínio 3 milímetros, essa liga foi soldada, compramos esse filamento, tá, metal de adição da mesma empresa que publicou o artigo, ou seja, com as mesmas características, e usamos aqueles parâmetros de soldagem, porém uma corrente de soldagem, alguns parâmetros um pouco mais, depois eu volto a explicar sobre isso. Usamos outros métodos de caracterização, microestrutura, identificação de fase, fizemos teste de tração e microdureza.
Well, speaking about the heat input, we intentionally choose this high heat input because we know the fundamental is that if you have the high heat input, then you actually accelerate the solidification cracks. So we intentionally wanted to create more and more solidification cracks in the structure. So the problem with that one is not only it increases the susceptibility of increasing the solidification crack, at the same time, it increases the porosity as well. So the porosity is something we can control with the parameters. But I'll come back to the porosity. Like porosity affected our results. That's why I'm mentioning the porosity here.
Bem, então a gente fez o seguinte, uma condição bem extrema de soldagem, a gente conhece todos os parâmetros de soldagem, porém a gente decidiu colocar uma situação bem extrema, como a taxa de aquecimento, ou seja, de calor no material, bem elevado, entendeu? Para que a gente pudesse construir um cenário que pudesse realmente produzir trincas de solidificação e também porosidade. E a porosidade é um processo que pode ser controlado facilmente, já as trincas não. Então, depois eu volto a falar sobre as porosidades também.
So this is the output. So we created two different wells. So one is autogenous, another one is heterogeneous. So autogenous was, we didn't use any filler metal whatsoever. So we just joined two 7075 sheets without any filler metals. And in heterogeneous joint, we welded the sheets with filler metal, and the filler metal was 1.7 weight% titanium carbide nanoparticle infused 7075 filler metal. So we have nanoparticle in heterogeneous joint, and we don't have any nanoparticle in the autogenous joint.
Então, você vê as duas condições que nós usamos, a condição primeira que nós chamamos de autogêneas, ou seja, nós não usamos o metal de adição, tá, proposto, você percebe as trincas, e a outra heterogênea, a gente usou o metal de adição, o filamento, com a composição química de 1,7%, tá, de carbonato de titânio, como vocês verem aí na apresentação.
And as expected, we got a large amount of solidification cracks in the autogenous joint, and we created a crack-free Aluminium 7075 welded sample with the use of only 1.7 weight% nanoparticle.
Como vocês veem, ou seja, quando nós não usamos o material de adição, trincas de solidificação em todos os lados, e a diferença quando a gente usou o metal de adição.
And if we look at the microstructure in autogenous and heterogeneous joint, so there is a big difference in microstructure. What we can see in autogenous, or let's say without the presence of titanium carbide nanoparticle, the microstructure in fusion zone is kind of like dendritic types, whereas the microstructure in the fusion zone for a heterogeneous joint is no longer dendrites but is equiaxed. Titanium carbide nanoparticle changes the morphology of the microstructure from dendritic to equiaxed.
Ou seja, quando a gente vê as duas condições, ou seja, sem um metal de adição que possui os carbonetos de titânio, nanopartícula, você percebe que tem uma zona de fusão dendrítica, tá? Você percebe as trincas, e em contrapartida, quando você percebe que foi usado o metal de adição que tem os carbonetos de titânio, você percebe uma estrutura de grãos equiaxiais, ou seja, não tem trincas, você viu que alterou totalmente a morfologia do material.
And we see a significant amount of porosity in both autogenous and heterogeneous joint.
E nos dois a gente consegue ver uma significativa quantidade de porosidade nos dois.
So if we look at the scanning electron microscope images for the fusion zone in autogenous and heterogeneous, so the basic difference in between those two fusion zone structures are these long and continuous phases that's present in autogenous wells. So we don't really see that kind of long and continuous phases in heterogeneous wells. That means we have titanium carbide nanoparticle in there. So it is understandable. It is kind of like guessed that somehow the titanium carbide nanoparticle prevented the formation of that long and continuous phase precipitates. Those are the harmful precipitates for the structure.
Se perceber nas imagens de microscopia eletrônica de varredura, você percebe que a autogênese, ele formou uma fase contínua, tá? E qual, em contrapartida, você não consegue ver essa fase, ou seja, as nanopartículas de carboneto de titânio foi suficiente para evitar essa formação dessa fase contínua na microestrutura do material.
And if we actually take one of the heterogeneous precipitates here in the area scanning and ADS mapping, and we see that this is one of those precipitates on the heterogeneous joint, and we see that the precipitates are mainly zinc, copper, and magnesium. We do have all those elements in the structure, but we see some traces of titanium all at the corners of the precipitate at like these different regions.
Ou seja, se a gente percebe, se faz uma análise de EDS dos precipitados, você percebe que o pequeno precipitado da condição heterogênea, tá? Percebeu que existe nesse precipitado elementos químicos como magnésio, cobre, porém, nos cantos desse precipitado você consegue ver titânio, tá? Titânio que advém dos carbonetos de titânio.
Now, we performed some mechanical properties as well, and we found that, well, first of all, we couldn't test the autogenous wells because of the large solidification cracks that we have, but we tested the heterogeneous wells, and we found the mechanical property is, in some cases is good, okay, in some cases it's not that bad, not that good, and they all failed in the fusion zone. But the main idea, and the 7075 is stronger. 7075 has an ultimate tensile strength of 572 megapascal, but what we got maximum is approximately 400 megapascal.
Ok, você percebe que as propriedades mecânicas ela foi feito uns testes de tração, percebe que continuou com as propriedades elevadas, tá, de 572 megapascal. Professor Kabir, I think you should run a little bit because the time is
okay. Yeah. Right. So I'll finish in 2 minutes.
Okay.
All right.
Go ahead.
All right, and all right, let's go back. Let's go. All right, I think I have only 2 or 3 slides. So the reason of this changes in the mechanical properties, as I mentioned before, that we used high heat input that created a lot of porosities in the fusion zone, and the fusion zone was the reason why we have such a low mechanical property.
Ok, apesar das propriedades mecânicas foram baixas devido a essa quantidade de porosidade, porque foi usado, né, inclusive os parâmetros mais críticos possíveis para criar porosidade.
And if we see the average fusion zone hardness, we found that the heterogeneous hardness is more or less higher compared to the autogenous well. So the microstructure, the ICAIC microstructure was even stronger than the dendritic microstructure.
Apesar disso, nós vemos aqui para a condição heterogênea, nós temos uma dureza mais elevada do que o outro processo, na zona de fusão.
Okay, so this is the hypothesis that we have, that presence of titanium carbide nanoparticle, it actually changes the precipitation morphology. So we found the trace amount of a very new type of composition that has the titanium in it. So we are guessing this new composition of precipitates actually does not lead the formation of continuous precipitates in the structure.
Ok, então a razão principal é que os precipitados, nossos precipitados, formaram novos precipitados, ele alterou totalmente a composição química desses precipitados.
Okay, so let's come to the conclusion. So we found that the titanium carbide nanoparticles in the fusion zone, they were effective in eliminating solidification cracks, and we proposed 2 mechanisms for this one. So that one mechanism is that the presence of titanium carbide changes the grain morphology from dendrite to equiexed, and it changes the morphology of the secondary phase as well.
Então, nós vemos que nanoprecipitados de carboneto de titânio foi eficiente em eliminar as trincas de solidificação, tá? O qual mudou a morfologia do material, ou seja, de dendrítico para ecoaxial, e além de que também ele mudou a composição química dos precipitados.
All right, and thank you so much. And these are the references that I used in this presentation.
Ok, obrigado. Thank you, Professor Kabir. We will finish right now. If you have some question for the audience, I'll take this question, okay? I'll take note of this one. I'll forward this question to your email, and after you can respond, okay?
Yeah.
Ok, pessoal, se você tiver alguma pergunta, vocês anotam, depois me passam essas perguntas e eu passo para o professor depois e respondo para vocês, tá bom? Que agora nós estamos para a próxima palestra. Thank you very much.
Thank you so much.
Okay, bye-bye.
Bye.